put out a previous video where I talk about using this ESP32 and a shift register, the 74595 shift register, to potentially build a DAC, D to A converter. I've made some progress. I've been playing with it for a long time. Solved some problems. I have some problems, right? I have some noise problems that I'm struggling with. So what I've done here is I've got it set up to where you can hear it, and maybe you guys can help me figure out where some of the noise is coming from. So the first thing I want to do is sort of go through the setup. It's pretty complex, so here we go. All right, starting with this laptop, I will be able to record the screen of the laptop. I'm not doing it yet, but the laptop has hooked to it an oscilloscope, so we'll be able to see the waveforms coming out of the DAC. The laptop is also connected through Bluetooth to the ESP32, the little ESP32 right there. So over Bluetooth, audio will go to the ESP32 via, what we talked about last time. The ESP32 is putting the digital data on the DAC. The DAC is then turning that into analog. The analog output coming out here is coming over to this PC. Great cord. The PC has a standard-ish sort of sound card in it. So it has a line input. And then I'll also be able to record its screen. And in that recording, you will actually hear the audio. And I'll be recording what I'm doing. With this camera, I'm going to record what I'm doing to the circuit. And then with the camera I'm holding here, I'm going to record myself. So okay, I think I have everything going. First thing I want to do is refresh our memories about the block diagram that I drew last time. I've got a better version of it. Last time I did this, it was really crude. So on that piece of paper last time, I drew this diagram upside down and in bad lighting. So this should be a lot better, easier to understand. But I got a lot of details going on here. The ESP32 sort of forms the digital backbone of the DAC, both the input and the digital output. Now, I talked about using I2S as the input, and that would probably be the best way to go once I get to doing high resolution 24-bit types of data. But for now, and since it's built into the ESP32, I'm just using Bluetooth. The Bluetooth is, it's 16 bits per channel, right? 44.1 kilohertz. CD quality audio. And that's what we're sending from the laptop. The laptop is connected to the ESP32 over Bluetooth. And let's see, show Bluetooth devices. Right, the R74 DAC here is the program on the ESP32. So the laptop is connected to it right now. So this part in software, So this part is implemented in software, the Bluetooth connection, which was pretty much handed to me by, libraries. I found an example of how to receive Bluetooth and pump that data into a data buffer. The data buffer, from the data buffer, we clock the data out. Well, I'm also converting, and where right now, I'm only doing the left channel. The right channel is just not being processed at all. It might be getting put in the buffer, but when I bring data out of the buffer, I'm only doing the left channel. I'm converting it down to 8 bits, just mathematically, right? And then based on a timer, we're pumping that data out of the ESP32 through the digital output stage that we went into great detail about last time in that previous video. Using write once to set and write once to clear. And that should be a T right there, not a 2. Sorry. To the shift register, which fans that number, that 8-bit number, right, out onto 8 individual digital lines. And then we get into the analog section, which is kind of what we've got over here, right? This is the digital data coming from the ESP32. It goes into the shift register. Now, I've only got one 8-bit shift register set up for this example, but the software that the ESP32 is running is shifting out everything. So even though I'm only using 8 bits of the left channel, the time it takes to send it all out, all 24 bits of both channels, is still in play. It's still clocking, it's just clocking zeros. And only one of the shift registers is hooked up. Then from the shift register, the digital outputs are coming over to the comparators. 2 comparators, 4-bit comparators each one. The comparator outputs are coming over to these voltage dividers. Each bit going to have its own adjustability. From there, we come into this resistor array, the output of which all the inputs are together, right? Or all the inputs come from the voltage dividers, and then the outputs of the resistors all come together to one point, and gray wire come over to this op amp. This resistor here is setting the offset voltage for the op amp, and this resistor here is the gain, right? The feedback, negative feedback resistor that controls the gain. From here, we're jumping it from having a voltage, a positive voltage offset. We're sending it through a cap to make it then, float above and below zero ground. And then this little pot here is an attenuator to drop it down to a voltage that's good to send out analog and drive an RCA input. The next part of this, I think, will be, first off, let's just listen to it, right? I want you guys to hear what it sounds like. This is the left channel of a 16-bit source, mathematically turned down to 8 bits. Let's see what we've got over here on this computer. I'm going to turn this volume down a little bit, so I want to be able to hear it, but I don't want the audio coming from that setup there, that computer, to get into the camera. Not nearly. Well, I can manage that in post, but I'm going to. So let me turn it down some anyway, though. . this is the line in properties. I couldn't get the line in, if you ever try to do this kind of thing, the line in wouldn't come up as available until I actually plugged the jack into the back of the computer. And this set of properties is where I figured out which color jack to plug it into. So that's what's going on here. Being recorded on this computer using OBS. So it's recording now. Let me go ahead on this computer over here. I'm going to start a track in Amazon Music. And this is also the oscilloscope. Let me show you. The oscilloscope is just permanently sort of hooked up here. This is after it's converted to analog, right? But before it's attenuated to go over to the computer. So this is a pretty strong signal coming right off the op amp after it's converted to analog, after it goes through the cap. And let me find Amazon Music. And let's listen to this little royalty-free track. The other channel, the scope, the yellow channel. I'll quote the digital lines. That's probably lost. Probably the voltages are really the same. It's the same as the big one. So one of those is clocked. One of those is what's the one called? Here, this is the most significant bit. As I come down the line, see the voltages drop in half from each other. That's what the voltage dividers are called. Those plots have all been tuned so that the voltage drops in half. So all those voltages come over to these resistors. And on the other side are summed up, added together, and amplified. That doesn't sound too bad, right? Doesn't sound great. It's just 8 bits. But there's noise there that's not necessarily apparent. Let's see what this one sounds like. Play with the volume control a little bit because right now it's set up where I can definitely turn the volume up to where the DAC will clip internally on some tracks. Depends on the track, which is really kind of shitty. You can see it flatten out there. Well, honestly, that could also be still. changing the number, right? Changing this volume control is varying the digital number that is being sent over Bluetooth. The ESP32 is taking that as number and then we're converting it down. Okay. So now let's get a little more into the technical stuff. And I've got a signal here that's pretty cool. I found this out on Amazon Music. This is a 40 hertz. It's a triangle wave at 40 hertz, and this is what it looks like on the scope. And I can barely hear it, but it should be a very low frequency tone, clean sort of tone when you're listening to it, and what OBS should be recording on that other computer over there. And sort of look at what the signals look like that produce this tone. You go down here to some of these smaller there's one of your smaller signals. The one above that. While I'm on one of these small signals, let me change the volume. That's interesting to watch it deal with that. Ooh. See, that causes some. Alright, I'm going to change the volume. Drive the clipping. So I probably really shouldn't be able to drive the clipping. I need to probably lower the voltages of all of my voltage dividers. But you hear that? There's static in it, in the ring. That sounds pretty decent. Let's go down and let's go over here to some of these other test tones. The good old trusty bunker analog. Start with a sweep for the fun of it. And this bunker analog stuff is down a good bit volume wise, and that's probably why I sort of tuned my DAC and it'll clip on other tracks. Channel 2, bring it up a little bit. Now you can see some of the noise. Some of that, there's a good bit of noise there. But also some of that is just that, we're only on an 8-bit DAC here. So you should be able to see the stair step in the waveform. Of course. Turn it up over here a little bit so I can hear what's going on. sizzle in it. You get one of these other steady tones. You know, you shouldn't really be able to hear that sort of. It should be a hum, not a buzz, right? 60 hertz. Tone in it, but there's something on top of it, right, that should be there. Let's speed this up a little so we can kind of see the details of it. Now, the jitter is another problem, a different problem. Not sure, and that jitter is audible. You can hear it. I'm not really sure what is going on with that jitter. It may have something to do with my software, although I'm not sure what it is. I'm not sure why. But then the sizzle, there's also a sizzle in it. You see these, all this fuzz on the line? It shouldn't be there. You know, it's on the yellow line too, and it's like, even if you like probe ground. It's like almost everything you do can cause noise. Now, it's been worse than this. Well, that's me. Shorten two lines together is going to cause terrible things to happen. As a matter of fact, let's go ahead and show a little bit of curvature in here in this sine wave. You know, slight variation. The pots, when the pots get out of calibration, that's when you see problems like that. Actually, I want to go back to the triangular wave because it's more clear at what's going on that than it is on a sine wave. Hopefully I can do that quickly here. Here we go, yeah. So let's show you what it looks like when you vary this most significant bit here. Man, can't get on it. Hard to get that screwdriver in that groove. I need that tool that is designed for these trim pots. And you can hear it too, right? You don't just see it as that voltage. If you go too high with it, you hear the distortion. Try to get it back. Well, it's so hard, it's a little bit touchy. So each one of these pots, in combination with this resistor over here, the comparator, the output of the comparator is open collector. So when the comparator senses that it needs to go low, it slams it to ground. It's your responsibility to pull it up to the voltage that you want. So that's what's going on with these resistors. These are all the same value right now. And these resistors, right? We're creating a voltage divider that pulls the signal up to the desired voltage. And then when there's a low, the comparator slams it to ground. So I'm running on a 16 volt supply. That would mean that probably, and that means that the op amp is getting a, well, it's on a 16 volt supply, but the input, it has an artificial ground reference that's at 8 volts, right? So you're tricking the op amp into thinking that it's in a positive and negative world. The same thing kind of happens on the way into the op amp. The voltage that's being put into the op amp is actually running up around, you know, probably in this case, it's running up around 7 or 8 volts. So this most significant bit here would be swinging, well, it's on the scope. What is it swinging between right now? That's channel 1. Channel 1's at 1 volt per division. So 1, 2, 3, 4, no. 1, 2, 3. That means that if all the bits, if channel 1 is going to be running at 3 volts, that means that if all of the bits added together would be running at 6. So if they were all high at the same time, the voltage coming out the other side of that resistor network, right, would be 6 volts. So you want your most significant bit to be half of the total potential of the DAC. And that's what these voltage dividers are doing here, right? Is controlling the voltage that gets sent to the summing amplifier when the bit is high. Now, this is really stable compared to the sine wave. I have no idea why that would be the case, but and then that glitch you heard there, that could be the buffer either overflowing or underflowing. And that's a jitter problem. There was a little shift there. That's probably a jitter problem. That could also be a triggering problem. So there's some things, right? There's some things to figure out. But I think it's the sort of general noise issues that I don't really have a good explanation for. Seems like there's digital noise that I don't have a good explanation for. Well, I would say that one of the primary problems here is that this thing's built up on a breadboard, you know, and breadboards have a lot of capacitance, you know, and there's a lot of potential for poor connections. That's the lengths of two resistors getting together. I worked on this for a while to get it as clean as it is before I started this video. So, but you know, sitting around on this breadboard for a few days, you come back to it, and it's, you know, it's pretty squirrely. Connections, these wires get loose. So I think my decision point is, do I want to spend the money to get boards delivered, you know, from China, PCB way or something like that, to see how much of my problems here are, sorry, I'm trying to think about this at the same time. I'm trying to bring up the PCB editor so that you guys can see the board layout that I've created. And I don't know. Okay, here it is. So I'm trying to decide whether I want to send off for some of these PCBs to see how much of the problems, see how much of what we're hearing noise-wise, is related to the breadboard, right? How much of this noise am I gonna ever be able to get rid of? You know, and there's also other things that could be at play, like counterfeit components, for example. That op amp is supposed to be one of the TI ones, the one that's real famous in the audio community. Can't think of the number. But the little Texas on the TI Texas is pretty smudged. I'm not sure, it might be counterfeit. So if the op amp might be counterfeit, I mean, maybe the comparators are, or maybe I didn't source a good comparator. Maybe I didn't pick a good comparator, one that's clean, right? A comparator should not pass any noise from the digital input onto the output. That's the point of it. Well, that and to jump it to a different voltage. I mean, the comparator can run at any voltage, right? So how much of this is a poorly designed circuit? You know, maybe it's just not a good design. It's possible that I need to work on my voltage dividers. I need to make sure that the comparator has enough clamping power because it can, you know, the comparators are capable of clamping 100 milliamps. Maybe the voltage dividers I have set up are running a little too hot, right? Where the comparator can't really clamp it all the way to ground cleanly without there being a ring. You know, maybe a lot of what we're hearing here is ring on each bit, maybe some bits more than others. So a lot of stuff in play. You know, filters could be put in certain spots, maybe a filter on each bit to filter out high frequency noise. Above, but I mean, you know, if we can hear it, I'm not going to be able to filter out things above 20 kilohertz and it, you know, they come off of this, not be able to hear it. Do some, let me do a 1K tone. Now you hear that sizzle? Sizzle shouldn't be there. It sounds like, oh, the scope's not working for some reason. It sounds like clipping, but it's not. That jitter shouldn't be there. Why is it so much worse on this track than it is on that triangle wave track? That's just strange. Also strange. So I'm going to give it more amplitude. Drop me some comments. Let me know what you think. Is it worth pursuing? Just a bad idea? What could make it better?